Hi guys, thanks for stopping by Pete's Garage. Well, we're going to start talking about camshafts. And camshafts are one of the parts of your engine build where planning is the key. Now I've talked about planning before, choosing your crank, pistons, rods, rings, those kind of things. But a camshaft is very important for planning because you can literally tell how this cam or how your cam is going to perform when you look at the numbers and how you have it ground or purchased already ground. The proof of the performance is in the numbers, and understanding those numbers is very important. So what we're going to talk about in this video is this. We're going to talk about, first we're going to talk about lift. There are a couple different kinds of ways of measuring lift. There is the ground lift, or the way it's ground, and the actual delivered lift, the lift delivered to the valves themselves. There's a duration. Now there's an advertised gross duration, which is the manufacturer will advertise, but there's also a importance to understanding what the cam is going to deliver at 50 thousandths of tappet rise, and I'll explain why that's important. We'll look at the LSA, which also known as the Lobe Separation angle, and this is important to understand how your cam is going to perform under different situations depending on you're going to drag race, you want torque, performance, etc., and how it's going to idle. Then there's also the ICA, which is known as the installed centerline angle, and this is important to understand when you're going to degree a cam and install it and degree it with your crankshaft. So talking about all that, we're also going to talk about solids versus hydraulics and the lifters. And the cams, we're going to talk about a roller versus a flat tappet cam, when you want to use those and what the requirements are, or what application is best for a roller or a flat tappet. We're going to talk about lash and preload. Once you install your cam, what the lash and preload has to do and how you have to consider that when choosing your cam. And finally, we're going to talk about the, what are we going to talk about here? Oh, I'm sorry, cam cards. When you buy a cam, the card that comes with the cam, how to read it. What does it mean to you? What is it? How can you read the cam card and tell you what to purchase for the remaining components of your valve train? The cam card is very important. If I didn't have such messy handwriting, I'd be able to read it. My handwriting is terrible. But let's get started. Let's start talking about lift. Well, before we do that, let's look at a camshaft very close, and I'll just identify the parts really close. Then we'll look at some pictures, and I'll explain the lift and how you measure the lift and why the lift is important to measure at certain points of the rotation of the camshaft. Identifying parts of the cam are really simple. In a regular V8 or V6 kind of center cam, the cams are all pretty similar. Overhead cams are a lot different, but they have the same kind of nomenclature for the parts, and you basically have a few different parts. You have the journal surfaces. You have a journal surface here, a journal surface here. Journal surfaces where the cam rides in the bearing inside the crank. You'll have some gears here, and this gear is used to turn the distributor gear, to rotate the distributor for the timing of the spark. You'll usually have a pin up front. The pin is used to align the cam gear and hold it in place with so that the timing of the cam gear is aligned with the crankshaft. You get a hole in the front for the bolt for the retainer plate and the timing gear. And some camshafts will have a hex right in the cam, and that just helps in turning it over once you have it inside the engine if you need to do anything. You have some oil holes just to help draining in the front or in the back of the cam, and this is where it sits in the cam bushing in the back of the engine. So those are the basic parts of the camshaft, and as you turn, depending on the rotation of your engine, you usually have an intake and exhaust. We'll talk about load separation angle in just a minute, but right now let's talk about the lift of a camshaft, and it all has to do with the lobe of the cam. You see you have a flat part or a base circle of the camshaft, and it comes up on the lobe, and this lobe right here is what we're going to start talking about, and this is where all the lift is. The shape of this lobe, the height, the angle, and the slope of the line and how fast it opens. That has a lot to do with the duration, lift, etc. Let's talk about lift right now. So the first thing we're going to look at is the lift on the camshaft. And what I've drawn here is a lobe. It's a cross section of the lobe, and what we basically have, the center of the cam is referred to as the base circle, and that's where the lifter will ride. It rides on the outside of the lobe. Then there's the bearing surface. If you were to look, you'd see the bearing surface where it rides in the bearing, and then you have the lobe itself on the camshaft. Now lift is one of the easiest and most basic term to understand. The word lift refers to how far the valve is opened off the seat in fractions of an inch. And in this example, I got it 318 thousandths of an inch. The gross lift, now there's two different kinds of lift. I mentioned regular ground lift. So this is ground with 318 thousandths inches of lift. The gross lift of a cam is actually, the lobe lift is multiplied by the rocker arm ratio, okay? As the camshaft comes around, as it comes around and rotates around the base circle, the lobe ramps up and the lifter displaces and it rises and opens the valve, and it does that until it reaches the peak right here, the peak of the lobe. When it reaches that, the gross peak of the lift, that's right on the nose of the lobe. The amount of displacement is actually the lobe lift of the cam. The lobe lift isn't the same as the amount of lift at the valve, since the valve is multiplied by the rocker arm ratio. Now most manufacturers have different rocker arms, different rocker arm ratios, because they're not really all created equal, because there's different push rod sizes, different kind of lifters. So the push rod side of the rocker is the closer side to the rocker's pivot point than the valve side, so the ratio gains lift on the maximum lift of the lobe. So if we were to look at this, if we were to look at an aftermarket or a cam lift here of 318 thousandths, and the average aftermarket rocker arms will provide a 1.5 to 1 to 1.75 to 1 ratio. So if we have a cam with a lift ground of 318 thousandths of an inch, and we put it to a rocker arm with a ratio of 1.5 to 1, this ratio of rocker arms will actually give us 0.477 inches of lift. That's delivered lift to the valve. If we put it to a 1.6 to 1 rocker arm, we'll get 0.506 inches of lift. Oh, I'm sorry, 509, I think. Right, 24, 5, 9, fine. 509 inches of delivered lift to the valve. And if we had a 1.7 to 1 ratio rocker arm, we would take this 318 thousandths, and the actual delivered lift to the valve would be 541 thousandths of an inch. So you can see that by you choosing a different rocker arm ratio, we can take the ground lift of 318 thousandths and increase it to 477, 509, or 541. So you can open the valve further by changing the rocker arm ratio and getting a higher delivered lift. Now that sounds fine, and you might say, I want to change in my rocker arms to get more opening on my valve, but there are other things to consider here. If you go from a 1.51 to 1.6 to 1, the things to consider here is, first of all, can your valve springs handle the additional lift or the additional compression? If you go from 1.5 to 1.6 or 1.7, you are taking that spring and you are crushing it a lot further than it would at 1.5. So what you're doing is you're putting an extra stress or further stress, compression stress on that spring, causing it to fatigue. The more you fatigue it, the faster you do it on a valve spring, the more chance you have of that spring failing. So simply changing your rocker arms to get a bigger valve opening is not as easy as just changing the rocker arms. You have to consider the valve springs and can they handle it. Also, if you open this valve up from 477 to 541, you're opening that valve an additional 70 thousandths, and unless you have a piston and deck clearance to handle that with clearance in the piston shape or piston design, that extra 70 thousandths could cause the valve to hit the piston head or the piston, and it'll cause it to hit it, bend the valve, and you'll drop a valve, blow up the engine. So you have to be careful when you choose rocker arm ratios or changing them just on that regular engine, just try and get more valve opening, okay? Now, actually, an engine's rocker arm ratio is given as a specification for that given style of engine, and the ratio is measured is not often exactly what the specifications indicate. You'll find that the actual ratio can be more or less a result based on the actual measured valve lift, and some things that affect the measured lift or rocker arm ratio are the push rod angles, push rod lengths, particular geometry on the cylinder head you're using. So you have to take that all into effect. An aftermarket rocker ratio is rated at 1.5 to 1. Do not usually deliver that exact ratio. and they sometimes deliver slightly higher ratio, and we're talking about all the variation in the actual delivery ratio, and the valve lift is going to, it's just an approximation, but it's pretty close. This is based on a rarely true assumption that the rocker delivers exactly as quoted. On the other hand, the lobe lift itself, does not include variables of rocker arm ratios and is a very precise number. This number is precise. This number is calculated and is very, very rough, so you shouldn't assume that this is going to be exact, because there are things that can affect it. Other things that can affect it, like the rocker, or the lifters, hydraulic, lash, all kinds of things in the valve train that can change this actual number right here. So it's very important to understand that. When you choose your rocker arm, you're going to get about that, and that's a good starting point, but it really should be measured in order to understand that. If you want to know exactly what the valve lift is going to be in a given engine combination, you need to actually mock it up, put it together with the camshaft and the valve train, and measure it with a dial indicator right on the tip of the valve. Just doing the math like this with the lobe lift and the rocker, with the rocker ratio, with a typically, we'll provide it's an approximation, but it's not close enough. As I mentioned earlier, there are a few other variables that can affect the actual valve delivered lift right here. This can be affected right here. Delivered lift can be changed, and the variations are really of little consequence to the street or mild performance engine. However, if you're going to build a serious racing engine, the engine should be put together and physically measuring the lift of the valve. So to measure the delivered lift, you have to measure that because to account for all the variables. So this is fixed. You can measure this calculation based on the rocker arm ratio is an approximation. So that's what lift is in at a camshaft. Now let's go ahead. We're going to move forward and talk about duration. So now we're going to talk about the duration on the lobe of the camshaft. And duration is different than lift. Lift measures how far the valve is open. Duration tells us how long the open cycle lasts. It's very simple. One is how far it opens, duration is how long it stays open. And how long it stays open is measured in degrees of rotation of the crankshaft. So the duration of the valve opening is measured in degrees of crank rotation. Pretty simple to understand there. It's measured from when the lobe starts rising, right here. So we got when the lobe starts rising, and when the lifter starts rising, and until the lobe finishes by dropping the lifter back to the same position. So your complete lift, or how long the lift is in degrees of crank rotation, is from when it starts to when it ends. Now, unfortunately, when advertising gross duration, or how long the valve is going to stay open, manufacturers tend to vary on this. And they advertise for one reason or another, just to try and advertise their cam as having more lift or more duration, or it's a better cam. And they usually do it in thousandths of an inch. So the duration of a cam might be advertised as 5 thousandths. At 5 thousandths, they'll use 5 thousandths to tell you their duration. Other manufacturers might use 6 thousandths as a basis for their duration. But it's a big difference. It's a big difference because I can say my cam will deliver more duration just by measuring it from 6 thousandths instead of 5. And it's kind of misleading, and you have to understand the difference between those two, because if you buy a camshaft and the manufacturer says it has a certain amount of lift while another manufacturer is less, they could be measuring at a different start point. I sort of illustrated that here. The important number to recognize when you're buying a camshaft is 50 thousandths of an inch. What is it at 50 thousandths? That's the common thing. What is it at 50? You're going to hear that a lot. Now, for the advertised duration numbers to be truly meaningful, the checking of the tappet rise, or used to calculate the duration, that needs to be known. Most cam manufacturers will provide this information in the specifications in the section of their catalog. They'll provide that. Now, a long time ago, camshaft companies they all agreed to list the duration specification at 50 thousandths tappet rise. They all agreed to this to make it equal. So we all have a meaningful point to know to compare them all at the same yardstick. And the check rise at 50 thousandths is what they all agreed on. So all of the companies that are using the same yardstick to calculate this specification, These numbers will provide a better basis or a good basis for comparison when considering different camshafts, okay? So I kind of illustrated that here, and you can see where if one company measures at 6 thousandths or at 5 thousandths, you can see the difference here, how it could be different lift based on the rotation cycle. But at 50 thousandths inches of lift, right here is where all companies agreed that, okay, we're going to give you the complete duration at 50 thousandths, tappet rise or lift, in order for you to make a better decision based on how the cam is going to perform versus other camshaft. Pretty simple. Duration, degrees of crank rotation. The most important thing you want to know is what is it delivering at 50 thousandths inch of tappet rise. That's duration. Now, let's move on to the little complicated part, and we'll talk about lobe separation angle. So now we're going to talk about LSA or lobe separation angle. Camshafts have 2 lobes per cylinder for a V8 with 2 valves. Depending on if you have an overhead cam, you might have 4 valves per cylinder. It requires different amount of lobes, but I'm just talking about basic camshaft design here. So you have intake and exhaust lobes for each cylinder, and here's a sample of an intake and exhaust lobe. We have your main center 0 degrees, and then you have your other lobe for the other valve going off at a different degrees, another separation. This lobe separation angle is measured in degrees, and it's measured in degrees of cam rotation. Lobe separation angle measured in degrees of cam rotation, whereas duration, a lift measured in degrees of crank rotation. So when we talk about lobe separation angle, we're talking about the rotation of the camshaft itself, okay? Now, without going into too much detail about this, and it's very, very complex, a key consideration when designing the cam is the lobe separation angle, and it's sometimes called the lobe displacement angle or lobe spread, depending on how you want to describe it. The definition here is simply the distance in degrees as measured on the cam. That's all it is, distance measured in the cam. It's found in the cam specs. That'll give you clues to the performance of the characteristics of the grind on that particular camshaft. But camshaft manufacturers are pretty sharp, and they know what they're doing. Most camshafts are going to have a ground LSA or lobe separation angle of around 104 to 115 degrees. That's going to be pretty standard. There will be variations on that, but the key thing to know here is that you have a degrees of cam rotation, your lobe separation angle. Knowing what this angle is going to tell you how your cam is going to perform. Obviously, if these were both straight up and down and the intake and exhaust valve were open at the same time, it wouldn't perform well, it wouldn't work at all. Likewise, if they were spread too far apart, it would not work well at all either. So around 104 degrees to 115 degrees is a sweet spot. Now, without going into a huge amount of detail on the calculations of these, what I'm going to do is I'm going to draw a quick chart that'll show you the difference between the crank rotation, cam rotation, lobe separation angle, and what you can look forward to or look for in your particular application. Okay, I've put together this chart really quick to kind of show you the difference between lobe separation angles and what they mean to the performance of the engine. You have a narrow separation where the lobes are closer together, or a wide separation where the lobes are further apart, and what they mean to different things. Now, first, for the intake valve. For the intake valve open, the intake valve is going to open earlier in a narrow separation, later on a wide. Same thing with close. It's going to close earlier, and on a wide, it's going to open close later. Exhaust opening. Exhaust opening is important for the response of the engine, and if you have a narrow separation angle, it's going to be later, earlier on wide, and they're almost opposite for everything. Overlap. When you have a narrow lobe separation angle, and you'll have more overlap, meaning that the 2 lobes will overlap. That red in there kind of indicates how much they overlap. So the closer they are together, the more of the lobes will overlap, and you'll get less with a wide angle. Cylinder pressure. If you're looking to gain cylinder pressure, run a higher compression engine, you're going to gain cylinder pressure with a narrow lobe separation angle. You get less with a wide. Idle quality. If you're looking for good idle quality, idle quality is going to be worse with a narrow one because the valves are going to be open at the same time, so you get a worse idle quality. It'll be better with a wide separation angle. A vacuum, if you need more vacuum, same thing with a narrow. Narrow, you're going to get less, you'll get more with a wide separation angle. Torque curve, now if you're racing, torque curve is important. If you're towing, torque curve is also important. So with a narrow lobe separation angle, you're going to get a sharp peak on your torque curve. Wide, it's going to be flatter. So sharp peak, drag racing, sharp torque, flatter, towing, that kind of thing. Peak torque, how much is going to develop peak torque for the engine? You're going to get more from narrow, less on the flat, or less on the wide. Sorry, I'm reading that flat up there. And RPM, if you're looking to get RPM out of the motor, depending on the capability and the size of the engine, when you have a narrow lobe separation angle, the RPM is going to drop off because you're going to start to get something called, well, kind of related to the valve springs with valve float, but it's going to drop off because you can only keep the valves open together at the same time before you start losing the ability of the engine to keep up high RPMs. If you want to get high RPMs off of the engine or out of the engine, you have to use a wide separation angle because it'll hang on. While the lobes are separated on the camshaft, the valves are going to be completely closed while the other one's open, so it's going to hang on at higher RPM. You won't get any float at higher RPM. So that's really quick on the lobe separation angle, what you can look for when you're buying it, and what your application really is going to demand. Now, before we go and talk about flat tappets and rollers, all the other stuff, one last thing is that we're going to talk about the installed centerline angle of the camshaft. That's when you degree your cam, and while that's important, then we'll go into the other details about flat tappets, rollers, hydraulics, solids, that kind of thing. So now we talk about the ICA, or the installed centerline angle of the camshaft. And this is a Camshaft Lobe. I know it's not that great, but I'm not an artist and never claimed to be one. So we very simply have a lobe with a center line, and a 0-degree center line being marked in the center line of the lobe. Now sometimes there's a confusion between the lobe separation angle, LSA, what I just talked about, and the installed center line of the camshaft, installed center line angle. Both terms, they have to do with the angles of the lobes in reference to the peak of the lift point, and they're somewhat related, but they're two entirely different measurements. The lobe separation angle that I just talked about is how far apart the lobes or the peaks of the point. So you have a lobe measures the difference between the peaks, and that is determined as soon as the cam is ground. As soon as the cam is ground, the lobe separation angles, lift, duration, everything is determined as soon as it's ground. Whereas the installed centerline angle is different because the installed centerline of the camshaft is how it relates to the crankshaft, which is different. It's a measurement of the cam phasing relative to the position of the cam to the engine's crank. And this measurement is usually referenced by the crank degrees from top dead center at which the cam lobe reaches max lift. So the installed center line has to do with the crankshaft top dead center of the cylinder at which top dead center of the cylinder of which this lobe is reaching maximum lift on the valve. Probably why they're so confused is that the numbers turn up in a range, kind of a range of values. A cam ground with 110 degrees of lobe separation will read a centerline angle of 110 degrees if it's installed straight up. So this, grab my other marker here. So if this is installed 110 degrees, it's installed straight up. That's with no advance whatsoever. Most cam manufacturers will grind their camshafts with a 4-degree advance on most of the on the lobes. So you'll get an advanced 4 degrees automatically when you grind it. That's most aftermarket ones. They'll have an advance built in. Advancing the cam makes the valve events happen quicker or sooner in the rotation cycle, and it generally favors a low RPM operation. It helps with idle quality, cylinder pressure, vacuum, lower speed torque, etc. Retarding the cam or taking the lobe separation and the installed centerline angle, retarding the cam timing to the crank deteriorates the characteristics. So, though in some cases you might want some high RPM in cases retarding the cam can enhance it in high RPM racing conditions, but usually you want an advanced little bit to improve those characteristics, handling characteristics of an engine. The real thing here is, or the thing to focus on, is that advancing the timing on a camshaft will almost always help improve all of the performance characteristics like low RPM, idling quality, cylinder pressure, etc., as I showed in the chart earlier. But most of the time, retarding the cam will get a little gain of anything if you retard the timing. So if you're going to install it straight up, you're automatically going to have a 4 degrees of ground given to you by the manufacturer. and that's going to help with engine performance right off the bat. Now, when you degree your cam, it's all based off the 0 degree straight up alignment of the number one top dead center of the number one cylinder, and going through that is going to be a whole different video, because timing your camshaft with the engine and advancing it has become very easy, because sprockets for camshafts and timing with the crankshaft sprocket has become very easy, and they're marked, and I'll show you that real quick. I'll install a camshaft and show you how that's easily adjusted just by the manufacturers giving you a gear that has it listed right on the gear. So now let's talk about our different hydraulic tappets and hydraulic solids and flat versus solid tappet cams. Okay, now I'll go over the solid versus hydraulic lifter and the roller versus flat tappet camshaft real quick. It can be pretty involved, but I'll just go over the basics here so you get a general idea of what you're looking for. First of all, comparing the specs of a solid versus hydraulic camshaft or hydraulic lifters is not as easy as it first appears, because while it seems like the specifications for both would be the same, they really aren't. We begin with the advertised duration numbers. Solid lifters and hydraulic lifters are rated completely different standards. For example, like a Comcam's line, the hydraulic rated for duration at 8 thousandths lifter rise, where solids are typically measured at 20 thousandths lifter rise. So immediately the lifters are measured differently at different thousandths of inch or different amount of lifter rise for each one. So you're measuring them differently, although they're not significantly different the way they look or the way they function. They're measured differently because the hydraulic one has to is met solid, while the solid one, hydraulic is met solid, while that's confusing. The hydraulic is more solid, and the solid, because the solid has to make up for the lash of the valve and the rocker arm. Comparing a solid to hydraulic by advertised durations, like comparing apples to oranges. In regard to lift, things are a little bit simpler, but then again, not a direct comparison to the specs would be just misleading. The lash needs to be accounted for and subtracted for a solid cam's specs to arrive at the true lift of the valve, and which can be compared to hydraulics cam specs. So they got to be measured differently. Finally, we have, and I talk again, subtracted. You have to subtract the left out of a hydraulic, and you don't out of the hydraulic. Solid subtracted. I talked before about measurements at 50 thousandths of an inch, and this is where it's important. With a 1.5 to 1 ratio rocker arm at 50 thousandths of an inch of lobe rotation or cam rotation, the solid lifter is usually measured at 50 thousandths of an inch, but the hydraulic is measured at 33 thousandths of an inch. And this is because the solid duration, and it's a 10% loss in the measurement of this, because with the solid, the lash take up some of the lifter's motions before there's any valve motion. The solid's duration at 50,000 reads duration as if it was taken at 33 thousandths on a hydraulic duration at 50 thousandths. And again, it's a 10,000 less in duration. And all it makes it all of this kind of thing at 50 thousandths lift makes it very difficult to exactly match a solid and a hydraulic lifter cam. So it's very difficult. It certainly can't be done by matching numbers on a cam catalog or on a spec card. So you have to understand what's going on between solid and hydraulic lifters, especially at 50 thousandths lift of the camshaft. Now, if we look at a roller versus flat tappet cam, now I have a roller cam here and roller lifters simply because I don't keep the parts laying around and I throw them away. All they do is sit around and collect rust, so I throw them away as quick as possible. But I do have some hydraulic and a roller cam here. Now, we come in two basic types, the flat tappet and the roller. We got a roller and flat. And both of these types, both of these can either be hydraulic or solid. But in the recent years, the roller cams have become more popular, and they're often a good choice when building high-performance engines. And the most obvious difference is the roller wheel on the end of the lifter here. The roller wheel on the end of the lifter is what makes the big difference in the lifter to roll over to cam lobe. while a flat tappet appears just to be flat. However, a flat tappet isn't really flat, it has a large radius built into the bottom. So if we look at this, you see this is what we got. A lifter, a roller lifter, will have 100% contact with the lobe on the cam. It's linear, it's flat, and it's straight across. So you can see that illustrated here. Since I don't have a flat tappet solid, I'll show you what the difference is here. Let me move this out of the way. The shape of a roller cam is more long, and again, I'm not an artist, but I'm just trying to do this to illustrate the difference. A flat tappet solid will be more egg-shaped, they're shorter and beefier, and they look like it would be better, but however, again, with the roller, you have 100% contact, and it's linear, and it's lower in friction because of the roller. The flat tappet cam with a solid lifter, the cam itself, the lobe, is going to be ground on a very, very slight angle, and the bottom of the lifter, I'm exaggerating this, is not really flat, it kind of has a dish at the bottom. And this is done so that as the camshaft rotates, the lifter rotates in the bore. The lifter rotates to keep lubricated and to keep an even wear on the camshaft surface and on the bottom of the lifter. That has different consequences. Now, what it does is the roller will have lower friction. However, a flat tappet solid will give you higher initial acceleration. So there's a give and take for each one of these. The roller keeps on accelerating with higher velocities. So if you have a roller cam, it's going to keep accelerating, and you'll be able to get much higher velocities out of it than the flat tappet. The flat tappet, it gets to while this is measured, again, remember at 33 thousandths, the hydraulic roller, this got higher velocities, but the flat tappet will get to the 50,000 sooner. So you're going to see that sooner out of a flat tappet solid cam. Also, a roller cam, you're going to get more lift and more duration out of it because of the reduction in friction and the way it can go for higher velocities. And while the flat gets to the 50 sooner, it's limited by the diameter of the lifter. If you look at this picture here, you can see the diameter of the lifter here is smaller, it's more egg-shaped. So the acceleration and the velocity of a flat tappet cam solid is limited by the shape of the lobe. Now, one of the biggest things to consider, and one of the major advantages of a roller cam versus a solid, is that a roller can take much higher spring loads. That's very, very important because since the flat tappet cam, you have metal riding on metal here, you have the lifter riding right on the cam, you have direct contact here, so the higher spring loads is going to push these two together, and they're going to see a very high amount of friction, and you'll either cause the cam to wear fast or you blow out the bottom of a lifter. I've seen the bottoms of the lifters just break right off and blow right through, and you lose oil pressure. So the higher spring loads of a roller cam make it more attractive because at higher RPM you can get the valve closed faster, whereas in a flat solid tappet cam you're not going to be able to do that because of that, and that's where the pressure becomes important. A flat tappet cam can only tolerate a very limited load between the cam and the lifter. The load between here is very limited. If you go past it, it's all over. You're going to blow it out. So those are the differences between the roller and the flat tappet. There's much more going into that, but if you need to get more detail and with your application, if you need help choosing that, consult the experts, call technical support for the cams, call Summit, Jegs, anybody. There's tons of experts to help you, so don't worry about all this information. I'm just trying to give you a difference between what a solid lifter and a hydraulic lifter is going to do for you and what a roller and a flat tappet cam are going to do for you. Basically the differences between those two. So let's put a camshaft in an engine. I'll put this cam in and we'll talk about lining up the degrees, advanced, retarding, the timing of the cam, and then I think that'll be it. Okay, so let's install this camshaft. I have a light coating of lube on all of the journals for the bearings where they're going to rest. I also have lube on the gear for the distributor gear where the distributor gear is going to engage the camshaft. And here's a neat idea. One of my viewers wrote, make it easier to install your camshaft, put a long water pump bolt in the end of the camshaft to help you install it. Good idea. I always learn something. I appreciate all your comments, and it really helps me out. So what I'm going to do is, I also have some lube on the inside of all my cam bearings to make it easier to install. So what I'm going to do is I'm going to start to put this in, and I'm going to put it in very gently. And the idea is to make sure you don't scratch any of the bearings as you're putting it in. You rest, set it in, then move it, move your hand out of the way. Slightly, you might have to slightly turn it to get it over the next bearing. And as you get towards the end, it gets a little more difficult, but it's not that bad. You know, make sure you don't drag the cam lobes across the bearing surface so you don't scratch the bearing surface. Lightly turning, holding on, getting right to the end. A little turn, a little lift, and there we go. Take my bolt out, and I will make sure that the cam turns nice and smooth, and it does, doesn't bind up anywhere. Now I can put my plate on, my retainer plate, and I'll torque that down, and then we'll get to the gears. As I'm putting in these bolts, I just wanted to put a quick note in here. I'm using a little bit of red thread locker, just a little bit on the bolts for my retainer plate. It's a good idea to put just a little bit on there. And a little bit of Loctite. If you ever tasted Loctite, and I don't know why you would, but I have by accident, tastes a little sweet, might smell a little sweet. If you taste it sweet, one of the main ingredients in Loctite is saccharin. I've been to the Loctite facility where they make Loctite in Switzerland, and it's kind of neat. It really smells like they're making candy in there. So there it is. I'm going to torque those down, and we'll put the gear on. Now I talked about manufacturers making it very easy to advance and retard your timing. And you can see on this gear, and I'll try and show you, you have 0 for straight up 0 timing. There's A2, A4, A6. So in 2-degree increments you can advance your timing. And then there's R, 2, 4, 6, 8. You can retard the timing. So if you want to advance your timing, it makes it very easy. You just line up the advanced mark with your crank sprocket and the keyway and put it on that way. Now my camshaft is already ground 4 degrees ahead, and I want to advance it another 4 degrees for a total of 8 degrees advanced timing on my crank for my cam. So I'm going to take the A4 on this part, on my crank gear, and I'm going to put that, I'm going to line that straight up with the, and I'm going to turn this just a little bit, I'm going to line that straight up with my sprocket, right on the keyway, just like that. Now I'm going to take my cam gear. Now you can notice the cam gear has a little dot on it. They'll have a little small dot right there, and that's the lineup. You line up the cam mark with your timing mark. So I'm going to hold this straight up. I'm going to line, there's my dot lining up with the 4, and I will engage the chain to make sure that it's straight. Pull it up, line it, make sure the pin in the cam is lined up on nice and straight, and there we go. I have my 4 lined up with a dot, and I have my cam advanced 4 degrees according to the crank sprocket, and it's ground ahead 4 degrees, so I got 8 degrees of advanced timing on my camshaft. Cam gear is bigger than the crank gear because the crankshaft rotates twice as fast as the cam. Now, let's wrap this up. We'll look at a cam card. I'll show you how to read a cam card, and that'll be it for camshafts. So here is the cam card for the grind on my ComCam's cam. Now when you read the cam card, it's pretty simple. It's going to give you the part number. It's going to give you your serial number of the cam that you have, and it's going to tell you that it's camshaft for a Ford 351 Windsor 302 heavy duty HR so and so. It's going to also give you the part number, serial number of the cam, which matches. I had it ground. J&L Performance in Lancaster, New York is where I get all my parts from, and I work very closely with on every engine I build, because these guys are geniuses when it comes to building engines, and I rely heavily on them to help me, guide me in the right direction when I'm choosing parts, and they are fantastic. I'll put their number at the end if you want to give them a call, because they are fantastic. Now the grind. I had this ground a little bit differently, and I chose a pattern for the grind pattern, but the important thing here to know is we talked about what the lobe separation, how it's ground straight up. So I have 110 degrees plus 4, so I have 4 degrees built-in advance of the timing for the lobes. Now, valve adjustment. These are valve adjustments for hydraulic. I'm using hydraulic. That's a hydraulic cam with hydraulic lifters. It gives me the gross valve lift, taking into account the rocker arms that I've chosen for this application, and the intake can count on 0.576, and on the exhaust you can see it's 0.600, so I got a pretty heavy duty lift. And here's our duration. Now you can see I talked earlier about how manufacturers rate their cams. This one's rated at 6,000 of degrees. Some are rated at 6 thousandths of an inch. Some are rated at 5 thousandths of an inch. And here we have a 6 thousandths inch tappet lift being 293 degrees and 299 at 6 thousandths. Then it goes into talk about valve timing, and this is the important part. At 50 thousandths. At 50 thousandths is the common standard. When we have the intake valve open at 15, exhaust at 58, it closes bottom to top dead center 47 and 10, and it gives you more detail on the 50 thousandths, but even more specific. The duration at 50 thousandths. Duration at 50 thousandths, the intake is going to be 242 degrees, the exhaust is going to be 248 degrees. Duration at 50 thousandths. These specs are for the cam installed, so after you put it in at 106, the intake centerline, that's what's mean 106. It was 110 plus 4 degrees, so it's only 106, so you take off the 4 degrees. Installed at 50 thousandths. Lobe lift is going to be 0.36 or 360 thousandths. The exhaust will be 375 thousandths. And again, lobe separation 110 degrees. That's the cam that's chosen. That's how you read a cam card. Not very complicated, but there's a lot of information there that'll tell you how the cam is going to perform once you get it installed. So there we have everything you ever wanted to know about cams and less. And if you're thoroughly confused, don't worry, because so am I. It is a lot of information. It's very complicated to understand. If you don't understand it and you need help choosing a cam that's right for your engine, start at the planning stage at the beginning of your engine, choosing your cam, how you're going to use hydraulic. Are you going to use solids? Is it going to be roller? Is it flat tappet? All that stuff should be chosen ahead of time, so you're not scrambling to try and make parts fit at the end. If you don't know what to do, or you're not sure how to choose it, you don't want to go through all the information, try and figure it out yourself. There's a lot of experts that you can rely on. You call any one of the cam manufacturers, talk to their tech support, they'll help you choose the right cam. You can call Summit, Jegs, anybody that sells parts, and they'll help you choose the right cam for your engine. But you want to get them involved earlier on in the design process or the part selection process, so they have a chance to help you find a cam off the shelf that's going to help you work. Because if you need a custom ground cam, it's going to cost you a little extra money. So get them involved up front and work with somebody. I work with J&L Performance. The guy I work with, his name is Paul, and this guy is an encyclopedia. He has 50 years of engine building experience, and there's not a question I can ask him that he can't answer over the phone or give it to me within 5 minutes. So find someone you can rely on to help you build engines. Even though I do this all the time, I always rely on getting someone else's opinion just to give a sense check to myself. And as always, keep it clean. FM. I said FM before, and a couple people poke fun at me for saying FM too many times, but I'll tell you, foreign material, when you put an engine together, is the first thing that's going to cause a big problem. Of the hundreds of thousands of engines I've seen built and the thousands that I've torn down, none of them have ever failed because they were too clean. Being too clean is not a problem. However, FM inside is a problem, so always keep your parts clean. When you're done putting parts together for the day, cover your engine with a plastic bag, an engine bag, garbage bag, something to keep the FM off it, and make sure it's clean and dry. I hope that helps you understand more about camshafts and installing cams, the degreeing of the whole thing, how it all works together with the lifters, the ground lift, the ground, how it's ground, and how it means to the overall delivered lift to your valves, what it means to selecting springs, And while I'm mentioning that, when you buy a cam, more often the cam manufacturer will recommend springs to use. So if you're not sure how to choose springs, the cam manufacturer is going to recommend a part number or a spring number to use to make sure you get the life out of it. You're not going to beat the cam up, you're not going to beat the valve up, you're not going to break the springs, and you're going to get a longer life out of the engine. So make sure you follow all the manufacturer's recommendations on spring choices. They can even recommend push rods, rocker arm ratios, all different kinds of things. So read the instructions. Taking 10-15 minutes to read instructions can save you thousands of dollars and a headache of having to rebuild your engine. That's all I got to say. If you have any questions, let me know. Leave a comment, I'll answer them. Please keep them positive. You know, sarcasm is appreciated. I'm a real sarcastic guy, but it's hard to read sarcasm in some of the comments, so let's keep them clean, kind, and courteous to each other. And I'll answer anybody who has a positive or rational comment. I'm not going to respond to negativity or nastiness. So let's all be nice. We're all trying to learn here. That's it from me. And again, I hope this helped you. Have any questions? I'm glad to answer. I'll get you the answer. Here's Paul's at J&L Performance. Here's his phone number. Here's my phone number. If you have any questions, let me know. Thanks for stopping by Pete's Garage.